Two nations, one river, and a bridge that engineers said couldn't be built. Stretching 2.5 kilometers across the Detroit River, with towers soaring 220 meters into the sky, taller than a 70-story skyscraper, the Gordie Howe International Bridge isn't just a crossing. It's a monument to human ambition. This single corridor handles over $400 million in trade every single day. That's more than 25% of all commerce between the United States and Canada, the largest bilateral trading partnership on Earth. And for decades, that trade relied on a single aging bridge built in 1929. When the idea of a second crossing was proposed, critics called it impossible. Political battles raged for over a decade. Lawsuits piled up. Skeptics questioned whether two countries could cooperate on a project of this magnitude. But in 2018, construction finally began on what would become North America's longest cable-stayed bridge. At a staggering cost of 5.7 billion Canadian dollars, approximately 4.4 billion USD, this mega project would require over 7,000 workers, 2.5 million cubic meters of concrete, and engineering precision measured in millimeters. This is the Gordie Howe International Bridge, and this is how they built it. Before a single cable could be strung across the Detroit River, engineers faced an enormous logistical puzzle. How do you prepare two separate nations for the largest infrastructure project either has seen in generations? The project footprint is enormous, spanning 300 acres on both sides of the border. On the Canadian side, the city of Windsor saw the demolition of over 100 residential and commercial properties. Families were relocated, entire neighborhoods reimagined. But this wasn't destruction, it was transformation. The entire bridge was first built digitally using Building Information Modeling, or BIM. This sophisticated software created a complete virtual twin of the structure, allowing engineers to simulate stress tests, identify conflicts between components, and coordinate the work of dozens of international contractors before breaking ground. 23 kilometers of new access roads were constructed, highways that would eventually connect the bridge to Interstate 75 on the American side and Highway 401 on the Canadian side. But first, these roads served as arteries for the construction itself, carrying millions of tons of materials to the work zones. Soil compaction became critical. The ground had to support not just the weight of the bridge itself, but the colossal cranes, the concrete batch plants, and the temporary structures required during construction. Engineers specified compaction densities exceeding 95% of maximum dry density, tested repeatedly using nuclear density gauges. Beneath the surface, a hidden maze of utilities had to be relocated. Gas pipelines, fiber optic cables, storm drains, and electrical conduits. On the American side alone, utility relocation cost over $200 million and took nearly 2 years to complete. A bridge is only as strong as what lies beneath it. And for the Gordie Howe Bridge, that meant going deep, very deep. The geology beneath the Detroit River presented immediate challenges. Layers of soft clay and glacial till, deposits left by retreating ice sheets 10,000 years ago, sat above the limestone bedrock engineers needed to reach. Some foundation piles had to penetrate over 30 meters underground before finding solid purchase. 3 types of piles were employed across the project: Steel H-piles, driven deep into the earth by hammers delivering 300 blows per minute. Drilled shafts, massive cylindrical excavations filled with reinforced concrete. And the most impressively, the caisson foundations beneath the main towers. Each main tower rests on foundations measuring 35 meters in diameter, larger than an Olympic swimming pool. Excavators removed over 25,000 cubic meters of earth from each location, reaching depths of 20 meters below the riverbank. Then came the rebar cages, intricate lattices of steel reinforcement bars, some over 50 millimeters in diameter. Each main tower foundation required approximately 4,000 tons of reinforcing steel, tied together by hand in configurations precisely calculated to distribute the immense loads above. High-strength concrete, rated at 50 megapascals, nearly twice the strength of standard construction concrete, was poured continuously for days. The largest single concrete pour lasted 76 hours and consumed over 6,000 cubic meters of material. Interrupting the pour would create weak points, cold joints that could compromise the entire structure. As the massive concrete foundations cured, they generated tremendous heat, a chemical reaction called hydration. Internal temperatures exceeded 70 degrees Celsius, threatening thermal cracking. Cooling pipes circulated chilled water through the concrete mass, and workers wrapped exposed surfaces with insulating blankets to control the temperature differential. Rising 220 meters above the Detroit River, taller than Detroit's Renaissance Center, the twin towers of the Gordie Howe Bridge are architectural and engineering masterpieces. These concrete giants were constructed using self-climbing formwork systems, massive steel platforms that inch upward as each section is poured and cured. Every 4 days, the formwork would jump approximately 4 meters, beginning a new cycle. The process repeated over 50 times per tower, with precision alignment verified by laser instruments after each lift. The tower geometry is no accident. The signature Y shape, technically called a modified diamond configuration, was engineered to optimize the cable geometry. The angled legs spread the massive tension forces from the cables, channeling them efficiently into the foundations below. With the towers complete, the deck began its journey from both shores towards the center, a construction method called the balanced cantilever approach. Steel deck segments, each weighing up to 400 tons, were lifted by floating cranes and positioned with millimeter precision. But the true engineering artistry lies in the cables. The Gordie Howe Bridge employs 216 stay cables, each composed of up to 109 individual steel strands. These strands are bundled inside high-density polyethylene sheaths, protected from corrosion by injected wax and equipped with internal dampers to reduce wind-induced vibration. Each cable is tensioned to a precisely calculated force, some exceeding 10,000 kilonewtons. As cables on one side are tightened, the deck shifts imperceptibly. Engineers must orchestrate this symphony of forces, tensioning cables in careful sequences to maintain structural equilibrium. And then the moment of triumph. The final deck segment, fabricated with tolerances measured in millimeters, is lowered into place. Two nations joined by steel and concrete and human determination. But this triumph was earned through years of relentless challenges. The Great Lakes region experiences some of North America's most punishing weather variations. Summer temperatures soar above 35 degrees Celsius, while winter plunges below -25. This 60-degree swing causes steel to expand and contract by significant margins, factors that had to be engineered into every joint and connection. Wind posed constant danger. At 200 meters above the river, gusts regularly exceeded 80 kilometers per hour, strong enough to send unsecured materials flying and make crane operations impossible. During peak wind events, all work stopped. The project lost an estimated 180 days to weather delays over its construction timeline. Precision alignment became obsession. The two towers, built 853 meters apart on opposite sides of an international border, had to align with tolerances of just 5 millimeters. Survey teams from both nations worked continuously, using satellite positioning systems accurate to within 2 millimeters and coordinating through a joint control network. The bridge itself is only part of the story. On each shore, massive ports of entry were constructed, modern customs facilities designed to process up to 10,000 vehicles daily. Advanced inspection technologies include under-vehicle imaging systems, radiation portal monitors, and integrated license plate recognition. And embedded throughout the structure, a nervous system of over 500 sensors. Strain gauges measure stress in real time. Accelerometers detect vibration patterns. Temperature sensors track thermal expansion. This structural health monitoring system uses AI algorithms to analyze data continuously, predicting maintenance needs and detecting anomalies before they become problems. When the Gordie Howe International Bridge finally opens to traffic, it will transform not just transportation, but the economic destiny of an entire region. The automotive industry alone relies on this corridor. A single vehicle may cross the border 8 times during its production, parts flowing between American and Canadian factories in a precisely choreographed supply chain. Every minute of delay costs manufacturers millions of dollars. The new bridge will reduce crossing times by up to 60%, saving the industry an estimated $300 million annually. Beyond automobiles, agricultural products, machinery, electronics, and consumer goods worth over $150 billion yearly traverse this corridor. The improved infrastructure will boost cross-border trade by an estimated 15% over the next decade, hundreds of billions of dollars in additional economic activity. Sustainability was engineered from the start. LED lighting systems reduce energy consumption by 40% compared to traditional bridge illumination. Stormwater management systems filter runoff before it reaches the Detroit River, and the improved traffic flow will eliminate an estimated 10,000 hours of vehicle idling daily, reducing carbon emissions by thousands of tons annually. The bridge bears the name of Gordie Howe, Mr. Hockey, a Canadian who became a legend in Detroit, beloved on both sides of the border. In many ways, he embodied the spirit of this crossing: talent without borders, excellence without boundaries. 7,000 workers, engineers, iron workers, concrete specialists, crane operators from dozens of nations came together to build what critics once called impossible. They endured brutal winters, pandemic disruptions, and engineering challenges that pushed the boundaries of their expertise. And in the end, they didn't just build a bridge, they built a monument to what two nations can achieve when they work together. A structure designed to serve not just this generation, but the next century and beyond. The Gordie Howe International Bridge, an impossible dream, made concrete, steel, and cable.